Welcome back. In this new video about quality management, we're going to look at two very important parameters, which are the process capability ratio and the process capability index. Both parameters will help us define which processes are compliant. It means that is the process suitable to create a part within certain specifications, within certain limitations. Think about the tolerances that we have, the lower and the upper tolerance, and the process capability index will help us to define what the sigma level of the process that we are considering in reality is. First of all, when we look at the process capability, when we look at processes, they have to be capable. Now, the processes have to be kept under control using statistical process control, or SPC, and it's the perfect tool for it. Now, when we consider the SPCs and the control charts, we can see what's happening with the mean or the variability of the process, or when it deviates, and we can identify when we have to remediate the process or adjust the parameters or conduct some repairs. We determine the control limits, and the control limits are based on the mean and the variability of the sampling distribution. And they're basically not but determined from the design specifications. Now, ideally, the mean should be the same as the design mean, and the variability should be so that the production, the process, can produce a sufficient high number of good parts. Now, when we look at the design, we look at the tolerances, and of course, when we look at the tolerances, we have to see that we have specific lower and upper specifications. So when we say we want to make a part 255 millimeters plus minus 5 millimeters, we know it has to be between 250 and 260. Otherwise, the part does not comply with the tolerances and we cannot use it in the other parts. Now, when we are looking at the different elements, when we look at the process capability, we have to look at the graphs below here. We have two examples here. We have the first process where we are having a distribution of the parts that are being produced, and we see that we have the three sigma limits of the orange curve, and they're clearly between the lower and the upper specification. So basically this means that the process is capable at the sigma level larger than 3. So, larger than 1, which means that we have 3 sigmas to the left and to the right. Now, the second one is in fact more spread, and we see that even at the lower or the upper specifications, we still have a significant number of parts that will fall out of those specifications. So basically, the capability is lower than 1. We can express that by the process capability ratio. And the process capability ratio, C index P, is in fact defined or is defining the capability of a process. And a process is capable if it has a process distribution whose extreme values fall between the upper and the lower specifications. Now, as a general rule, we take plus or minus 3 standard deviations to the left or to the right of the average or mean. And basically, the definition of this means that the upper specification is at least 3 sigmas to the right of the mean, and the lower specification at least 3 sigmas to the left. And when we calculate this, we can calculate the CP, the process capability ratio, C index P, as the difference of the upper specification minus the lower specification divided by 6 sigma, which has to be larger or equal than 1. That's the one I mentioned before. So when I was speaking about the sigma level there, I was basically talking about the process capability ratio, which says that the process is performing at 3 sigma level. When we look at upper specification minus lower specification, we basically find that this is 2 times the tolerance. So when we add the 255 plus minus 5, we find there in the numerator that this is 10 millimeters. And 10 millimeters divided by 6 sigma has to be larger or equal than 1, which means that our process is capable. We are producing the major part of all the parts between the upper and the lower specification. The larger C index P is, the larger the process capability ratio is, the higher the sigma level of the process. Let's have a look at the examples here. We have a process capability ratio example. We have production limits here. The nominal value, what we want to have is 35 millimeters. Tolerance is plus minus 5 millimeters. I love 5 millimeters. It's easy to calculate. Process data, we have an average which is 35 millimeter, and our process has a standard deviation of 1.5 millimeters. We can already see that when we multiply sigma with 3, that is already 4.5, which is below the 5 millimeters already. And when we look at 10 millimeters, it looks quite good. So we can already estimate or predict that this would be a capable process. When we look at the upper level, upper specification limit, which is 35 plus 5, we have 40 millimeters. We have the lower specification limit is 35 minus 5, which is in fact 30 millimeters. And when we look at the graph, we see here a centered graph around 35 millimeters, and we see the lower and upper specification limits. When we put that in the formula, C index P is USL minus LSL divided by 6 sigma. We find that the CP is 40 minus 30, which is 10 divided by 6 sigma is 1.5 times 6 is 9. And we find that the CP is larger than 1, it's 1.11. So the process capability ratio is larger than 1, which means that the process is capable. Now this is already good, so we can start working with this process. It has a sigma level larger than 3, so we have at least 3 sigma, even a little bit more. But now we want to look a little bit deeper, and from experience we know that this is not always the correct way to do it, because we have to, or we will define a process capability index, which is C index PK. Now processors are capable when the C index P is larger than the critical value, the desired sigma level, and when the process distribution is centered on the nominal design value. So basically, X double, the average of all the sample averages, is coinciding with the nominal design value. Now, is that always true? Not necessarily. So when we are looking at the process, we can see that X double bar, the average of all those averages, can move to the left or to the right, can move to, let's say, to either of those sides. And when that happened, and we will see it in the following graphs, the distribution also moves. Now, what we want to know is to define what happens with the sigma level. Certainly, when we have processes in 6 sigma, we have to be sure that our process is still providing the outputs at 6 sigma. Now, when we look at the sigma level of the process, we have to, or we define the capability index, which evaluates the left and right S level or sigma level. And the formula is in fact that we look, or the C index P, or the process capability index, is the minimum value of the sample average, or the average of the sample averages, minus the lower level divided by 3 sigma, or USL minus that average divided by the 3 sigma. So basically we have seen where is the average moving and what is the distance to the tolerances, to the design levels, design values. So that's what we have to do here. And let's have a look at the first step, where we are going at the table. First table showing us what is the CPK and what is the corresponding sigma level. Now, when CPK is equal to 1, we see that we have a sigma level of 3, and we know how many pieces are out of tolerance and the parts per million out of tolerance. We see those. Now, when we have a CPK lower than 1, for example 0.67, our sigma level is only 2, and at 0.33 it's only 1. Now we want to have higher sigma levels. Of course, if we want to have a sigma level of 6 sigma would mean that the CPK would be equal to 2. But when we calculate it, we can see, for example, when the CPK is equal to 1.33, the sigma level is only 4. When it's 1.67, it's only 5. So basically with this table, we can identify the sigma level of the actual process like it is operating and see if we have to take measures, because if we are working in a 6 sigma environment, we have to be sure that the CPK is in fact larger or equal to 2. If not, we have a problem. So let's have a look at some examples here. We're going to calculate the process capability index, and the formula is still there. So let's have a look, and we see the first graph, and we see that the first formula, the X double bar minus the lower specification level divided by 3 sigma is 35 minus 22. So we see that in the graph, divided by 3 sigma, which is equal to 6. And we see that this is 2.167. We do the same for the other side, looking at the distance to the upper surface level or specification level, and we find that it's also equal to 2.176, which is already also larger than 2. Now basically this is correct, because what we have here is that our distribution, the elements that we have, is symmetric. So we can say that the CPK is the minimum value of those two. Both are the same. So we have a sigma level which is larger than 6. We could calculate it from the table, but basically we're happy. We have a production, we have a process which is performing at a sigma level higher than 6. Now, when we compare the process capability ratio, we can calculate it using the other formula, and we find exactly the same value. Now, is this logical? Yes, because in this case, we have a symmetric distribution. The average, or X double bar, is equal to the average, to the goal, to mu, and it is, of course, with the same deviation, standard deviation, that we are in fact having the same value. But what happens when our distribution moves to the left? Now our output is not 35, but the output is 32. And we have to bring those numbers into our formulas. And we see for the left-hand side, we see that now the value is not 2.167 anymore, but only 1.67. So the average moved closer to the lower specification, and it means that the distance is less. We are not at the same distance anymore, we are closer. So our distribution, we have more elements which will be produced below the lower specification. On the other side, we look at the comparison, the distance to the upper specification limit, the fact that we move to the left, it's very logical to see that we are basically farther away. So the value here will be higher. It's 2.67. So that's very good on the right-hand side. But we have to take the minimum value. And since the minimum value is a CPK, which is equal to 1.67, we find, when we look at the table, a sigma level which is equal to 5. So basically, we started with a 6 sigma process, but due to the fact that the output of the process is not 35, but 32, the borders, everything moves to the left, and we have a lower CPK value and a lower sigma level. So we really have to do something about this. Now let's have a look at the evolution in the other direction. Now we move from 35 to 40. So we move 5 units to the right, and we can do the same calculation. Since we move to the right, the distance to the lower specification limit becomes larger, and it's equal to 3 even. On the other hand, I move closer to the upper specification limit, which means that that distance is smaller. And when I do the calculation, I find a value of 1.33. Again, I apply the formula. I take a minimum. I take the minimum of the two, which means that the process capability index is equal to 1.33, and our process sigma level is only 4. So basically this helps us to find the actual level, sigma level of the process while it is operating. In this graph, we see the different elements together. We see the results when we move from 35 to 32, and on the other hand, when we move from 35 to 40. So basically, we can calculate the sigma level of the processes. Now, that's what I wanted to talk about, the capability ratio and the capability index. It's sometimes difficult to understand the difference. I hope this presentation gives you a clear view of what happens. Basically, once our process is operating at a value which is not equal to the design value, we have to verify what is the actual sigma level of our process. And if we don't have the sigma level that we want to reach, for example 6 sigma, then we have to remediate, we have to stop the process, and we have to adjust everything, and eventually we have to do some testing to see if we have parts that are also outside of the design parameters, outside of the tolerances, because they will not fit in the assembly line. So that was it. I hope you enjoyed this. I hope you understood it with all the calculations and the numbers. And I'm looking forward to seeing you in our next video. Thank you and bye-bye.